Hello trackers, Professor C here to talk about a force essential to understanding the nature of electricity. It's called magnetism. Have you ever played with a magnet? You know, they either attract or repel other magnets and attract certain types of metal like iron. Now, for a quick refresher course on how magnets work. The ends of the magnets are called poles. Magnets have a north pole and a south pole. Now, the north pole of one magnet attracts the south pole of another. Opposite poles attract. Now, like poles, like if you get two north poles and two south poles, like poles repel each other. Curiously, no matter how many times you split a magnet, it always winds up with a north pole and a south pole. Now here's a big one. The Earth itself acts like a great big bar magnet buried in the middle of the planet, except we're going to bury it upside down. So that the south pole of the magnet is in the north pole of the Earth. Remember, south pole of the magnet buried under the north pole of the Earth. Now, with this said, have you ever looked at a compass? The needle always points in the same direction, north. Why? Because opposite poles of two magnets attract each other. A compass needle is actually a magnet, and the north pole of a compass needle magnet is attracted to our imaginary buried magnet's south pole, which remember is at the Earth's geographic north. Remember, we buried our imaginary bar magnet upside down, and opposite poles attract. A compass needle can be moved away from a northward direction when another magnet or a piece of iron is placed nearby. This happens because the other object exerts a stronger magnetic attraction than the Earth's magnetic poles. Now, it's commonly known that metals like iron, they're attracted, and they want to make contact. But iron's not the only metal. There are others, like nickel and cobalt, that are attracted to a lesser extent, and some that aren't attracted at all, like aluminum. An object containing iron, like a paperclip, does not attract other iron objects by itself. But once a paperclip touches a magnet, it will attract a second paperclip. It's become magnetized. Once the magnet is removed from the first paperclip, it no longer attracts the second paperclip. Now this happens because the iron particles in the paperclip are composed of many small groups of magnetic atoms called domains. See, the domains are arranged in this kind of random pattern with the north poles and the south poles pointing in all directions. So their magnetic effects are canceled by each other. See, in this arrangement, the object is unmagnetized. However, when a magnet touches the object, voila, the domains line up with all the north poles and the south poles pointing in the same direction. See, when this happens, the object becomes magnetized. Remove the magnet, and the domains return to their random pattern. A magnet has an area around it called a field, a magnetic field. This is an area where its magnetic forces act. A magnetic field passes through other objects. For example, a magnet will attract other magnetic objects through paper, wood, water, and other stuff. You can see how this field affects other magnetic objects by moving a compass around a magnet. Now notice, the compass needle moves in different directions, or not at all, depending on where it is. Another way to visualize the magnetic field is to place a piece of stiff paper on top of a bar magnet. Then sprinkle iron filings on top of the paper. The filings will line up around the magnet. The line of filings form a model of the magnet's magnetic field. So there you have it, magnetism in under 5 minutes.